Hello, good afternoon. Apurv Ranjan. Hello,
Good afternoon, sir.
good afternoon.
Good evening.
Good afternoon, Chaitanya. I was just waiting for the audience. Okay, let's just wait for another one more minute. Okay, now welcoming to contact session 8. Just prior to your ensuing midsum examination, which is slated for 21st, the next Sunday. So today we are just going to have once again solving system of equations. Of course, you have seen in the last session by Gauss elimination method. Now that we are going to have the kind of back substitution method at the end, but then we are going to decompose the given matrix into two parts. That is, we will make the given matrix A to be product of L into product of L and U, where L is the lower triangular matrix and U is the upper triangular matrix. You are all very much aware of lower triangular matrix and upper triangular matrix. But here we are going to have three different methods by which we are going to have the decomposition, and then we are going to use ultimately to find the solution, namely the values of x through values of y. So where do you get the values of y from? We are going to see, because there is going to be not just the matrix equation is Ax equal to b. When you are having, for example, m by n system of equations, in m equations, n unknowns, you have Ax equal to b, where A is matrix of coefficients of order m by n, x is column vector having n components, say x1, x2, x2, xn, and b column vector full of constants b1, b2, extra bm. Therefore, here as A is going to be the product of lower and upper triangular matrices in a particular fashion based on the different methods that we are going to discuss about. Naturally, we will have a substitution introducing the variable y, so that you will have first a kind of matrix equation, something like your original Ax equal to b. You will have some Ly equal to b, and then you will apply on x, so that you will have finally the solution in terms of your x, which was the original system of equations in which you have the system. And therefore, how we are going to split them, how we are going to decompose into the product. There are three different methods, as I told you: Doolittle's method, Kraut's method, and Cholesky's method. Let's see in detail one after another. And Apurva Ranjan, hello.
Yes, sir.
In response to your mail requesting for old question papers or previous year's question papers for reference, I had immediately mailed to the coordinator, and it seems it is available in Taxila portal. Have you checked?
Let me just check it quickly, sir.
Otherwise, I will find out again if it is possible from my side. Anything? Of course, we don't have any access. Let us see if there is any access being given. Then I will pass it on to. Okay, so don't worry. Clear?
Mhm.
Okay. So that again, since it is going to have the portions covering the topics from CS1 to CS8, of course, as far as the syllabus is concerned for your midsum examination. And this is being just prior to the examination that you are going to face next week. I would suggest you that you can concentrate fully on CS1 to CS7. Okay?
Yeah, yes, sir. So just
Okay.
one thing, the question paper has not been uploaded on the
Oh, okay.
Takshila,
Anyway,
Takshila portal.
I will check with the coordinator and whether they will be uploading it, or is there any other way to make you see over there. Okay, if there is any link or something like that. If there
Yeah.
is any such cases, then I will put an announcement in the Teams. Okay, you can refer
Mhm.
to, right? Right. So you can concentrate on um, finding inverse using Gauss-Jordan method, solving system of equations by Gauss elimination method, particularly as I have been giving emphasis on its partial pivoting, because that gives more emphasis on it. It is also adds significance to not just by elementary row operations and then easily getting into echelon form and then go back to back substitution method, because it is already available in your school days itself. Therefore, there is something more that you have to learn from this class that you had done in the last session that I showed you towards the end, how Gauss elimination method, particularly under the context of pivotal partial pivoting, that is, we just make arrangement, rearrangement, and then once again for your reference, if time permits, I think there will be enough time. I will go back to the Gauss elimination again and make you understand fully. Okay. So, and also you can concentrate more on your linear dependence of vectors, linear independence of vectors, linear transformation, and of course the nullity, uh, rank of rank of the transformation, nullity of the transformation, dimension. Similarly, rank of matrix, nullity of matrix. All those things you can finish.
Eigenvalues also, sir.
Yes, Chaitanya.
I- Eigenvalues also, right, sir?
Yeah, fine. That's good. Yeah, correct. Definitely. Definitely, because it forms a major chunk of your new topic that it's quite easy that you find the characteristic equation as a determinant of a minus lambda equal to 0. You solve for it. Normally, as I have told you that in practice that you will not be given any equation more than of degree 3, but it is easy that you have to have one assumption and then you have the factor divided the cubic polynomial by the factor, so that you are left with a second degree equation, which is a quadratic equation in lambda, and solve for two more values of lambda. So corresponding to each lambda value, you need to find the eigenvector. Okay. And also you must be familiar with the eigenvalue properties. So using the properties also, some simple questions may be found. So these are all the topics that have been covered so far in the first 7 sessions in a nutshell. Okay, right. So as I mentioned, Doolittle's method, Kraut's method, Cholesky's method. Each one has got its own way of doing it, but it's like with the slight differences only. But you have to remember those formulae to find those entries of lower and upper triangular matrices that become the part of your decomposition to as to make the original matrix into two. Then, of course, matrix inversion is only going to be a kind of recapitulation, as I have been talking about. The emphasis being given to finding matrix, inverse matrix of given square matrix using Gauss-Jordan method, not by the method that you are already familiar with, which you have been um, doing in your school days, like A inverse equal to 1 by determinant A into adjoint A whenever determinant A not equal to 0. And one more thing that even though it is very easy and that you have done it in school days itself, solving system of linear equations using Cramer's rule. Okay, that's very important. Very simple. As you find delta, the determinant of the matrix of coefficients, then delta x, replacing the first column, namely the column coefficients of x by the constant column, you get delta 1. Then similarly, replacing second column only by constant, keeping first and third intact, you get delta y or delta 2. Similarly, delta 3, replacing the third column, namely the column which is having coefficients of z by constant on the which is on the right hand side of your equation. So you get 4 determinants in all: delta, delta 1, delta 2, delta 3. And you know very well x equal to delta 1 by delta, y equal to delta 2 by delta, and z equal to delta 3 by delta. Right. Now, look at this. LU factorization. We write square matrix A as product of lower and upper triangular matrices. Doolittle's method. What is L? What is U? L is lower triangular matrix with an emphasis on diagonal elements. Whenever we talk about diagonal, we mean only principal diagonal elements. Even though there are two diagonals, whenever we write diagonal, we mean only principal diagonal elements. Okay, so diagonal of L means diagonal elements of L is 1, means each of the principal diagonal elements equal to 1. That's it's given. That is LII equal to 1 or Lij equal to 1, I equal to j. Supposing you have a 3 by 3 matrix A, then what is your L? L is a lower triangular matrix. What is lower triangular matrix? You have above the principal diagonal element zeros, isn't it? You have below non-zero entries. Of course, there may be 1 or 2 zeros, but primarily you have only non-zero elements. Of course, zeros must be there below above the principal diagonal. But there is one condition here for Doolittle's method. They are not just some principal diagonal elements. They are 1 each. And U is any upper triangular matrix. What is upper triangular matrix? Above the principal diagonal, you have non-entry zeros, and below the principal diagonal elements, you have zeros. So here we are going to make use of some entries by which we are making the entries familiar with us. For example, when you write A equal to matrix Aij, that is how normally we write, isn't it? A11, A12, A13, A21, A22, A23, A31, A32, A33. The same way here also we will use L11, L12, the L11, L12, L13. L21, L22, L23, L31, L32, L33. Of course, when it is lower triangular, you have in the bottom, you have in the below the principal diagonal element, above the principal diagonal element, you have zeros. So you have L11, 0, 0. Then you have L21, L22, 0. Then L31, L32, L33. Isn't it? That is lower triangular matrix. So, but here for Doolittle's method, those L11, L22, L33 will be each equal to 1. Upper triangular matrix means you have beneath the principal diagonal element 0. So you have U11, U12, U13. Then you have 0, U22, U23, 0, 0, U33. Okay, right. Anyway, you don't need to contemplate everything in abstract, you are going to see now for yourself. Crouch method. In what way it is different? U is upper triangular matrix with diagonal elements of U each of the diagonal elements of U equal to 1. That is UII equal to 1 and L is any lower triangular matrix. So there is a difference between Doolittle's method and Crouch method in the sense that in Doolittle's method, we give importance to, of course, both of them are important, L and U. But there is a speciality, there is a special condition that it is not just L, it is not just U, but we are giving importance to L in the sense principal diagonal elements of L, each must be 1. U is U, upper triangular matrix. When it comes to Crouch method, it is just the other way around. We are giving importance to upper triangular matrix with principal diagonal elements each equal to 1. Lower triangular matrix is lower triangular matrix, right? Okay. And in Cholesky's method, it is now entirely different. U is L transpose. So your upper triangular matrix is the transpose of your lower triangular matrix. So these are the 3 different methods by which they have some kind of distinction to differentiate between them. Now, benefits of LU decomposition. So what do we do actually? You know how to solve. As I have already mentioned, AX equal to B. If it's a non-homogeneous system in general, and if it's homogeneous, AX equal to 0. Okay, right. A equal to LU, that's the system AX equal to B, which we are familiar with, is LU into X, isn't it? AX equal to B. So we have to have a substitution. Let UX is equal to Y. Then Ly equal to B, isn't it? So you have to make a substitution because you only know by reducing into echelon form by back substitution method, find the unknowns. If it is Ax equal to B, naturally straight away the values of X. But here, since there is a decomposition of given A into L and U, you have LUX equal to B means you cannot directly have the control of LU over X. So you need to have one matrix, one unknown matrix, isn't it? So you think of your inner part UX. Let it be some Y. Then Ly equal to B, isn't it? In the place of UX, you have Y. You have introduced. So Ly equal to B. So what's happening? B is already available in your question. Is it right? L you have found. So instead of A, there is a matrix. That is your L. So L applied on Y. So now you have the unknowns Y1, Y2, Y3. For instance, 3 by 3, just for understanding. You have B1, B2, B3. So you are able to now get, as usual, values of Y. Now go back to the first substitution. First assumption, UX equal to Y. Isn't it? First assumption. You take the second part first and then go back to the first part because B is available, L is available. You have some unknowns because of this assumption. You have introduced, let it be Y1, Y2, Y3. So naturally you can find whenever there is a matrix equation of this form to find the unknowns Y1, Y2, Y3 or Y1, Y2 or Y1, Y2, Y3, Y4. But as I have been always mentioning about the kind of in practice that you will have at the most 4 by 4, but more or less in general you will have 3 by 3. Okay. So anyway you will have the unknowns found. So now with that as constants on the right hand side, instead of your B, now that you are having instead of just the AX equal to B, you have UX equal to Y. Now that it is now serving as your constants Y1, Y2, Y3, and U is already found, we have decomposed a matrix, and you have the unknowns now, X1, X2, X3. So U, a 3 by 3 matrix, X, 1, X2, X3, the components of unknown vector X, and you have the constants already found from this matrix equation. So this is how we get back to finding the unknowns X1, X2, X3, or the vector X as a whole. Okay, that's all. So what's the algorithm? Step by step procedure. Solve first Ly equal to B to find Y. Then solve Ux equal to Y to find X. Okay. So this is what I have just told you, that you don't need to search for those things in abstract. You don't need to wander about. You are going to visualize what exactly we have meant by lower triangular, upper triangular. In general, we know in Doolittle's method, what does that LII equal to 1 mean? And in Kraut's method, what do UII equal to 1 mean? Isn't it? That is how they are getting distinguished, isn't it? Right. So just look at the factors. L, U are defined as L equal to, just look at what did we say in theory? L means it is a lower triangular matrix. So naturally, above the, here of course you are given an example of a 4 by 4. Above the principal diagonal elements, you have zeros. So these are, so this is a lower triangular matrix. So what are the entries of L? So below the principal diagonal entries, in fact, including the principal diagonal elements, it should have been L11, L22, L33, L44. This is L21, L31, L32, L41, L42, L43, and so on. But what is the specialty in Doolittle method? L11 equal to, L22 equal to, L33 equal to, L44 equal to 1 each. Right? That is where Doolittle's method comes. And then at the same time, in Doolittle's method, when this is the lower triangular matrix L, simultaneously, what is your U? It is just an upper triangular matrix. That means below the principal diagonal entries, you are having zeros. So what are the upper triangular matrix then? U11, U12, U13, U14, 0, U22, U23, U24, 0, 0, U33, U34, 0, 0, 0, U44. That is Lij equal to 1 for I equal to j, Lij equals 0 for I less than j, Uij equals 0 for I greater than j. So don't get confused with I less than j, I greater than j means here, what's the meaning? See, Uij equal to 0 for I greater than j means, see, you will get here actually U31, isn't that? U31. So 3 is greater than 1. U32, 3 is greater than 2. So only those entries will become 0. But anyway, don't just confuse yourself. I less than j, I greater than j for which one? For L or U. Don't think that way. For lower triangular, upper entries above principal diagonal should be zeros. For upper triangular, entries below the principal diagonal should be zeros. That way you remember. But when it comes to decomposition of the given matrix into the factors L and U, you have, by Doolittle's method, principal diagonal elements of L will be 1 each and U is U only. And in Krauss method, it's the other way around. You just see that principal diagonal elements of U will be 1 each. So you have 1, 1, 1, 1. But look at here, in Doolittle's method, upper triangular matrix is upper triangular matrix. But here in particular, in Kraut's method, U11, U22, U33, U44 equal to 1 each. And lower triangular matrix is as usual. Whereas in Doolittle's method, upper triangular matrix is usual and lower triangular matrix is having the special condition that each of the principal diagonal entries is equal to 1. Okay. Cholesky decomposition is a technique that is designed for a system where the matrix A is symmetric and positive definite. So the Cholesky decomposition is possible only when the given matrix is symmetric. And positive definite, of course, means all its eigenvalues are positive. Yeah, of course, we have the nature of quadratic form that we don't need to go deep into. Positive definite, positive, negative definite, and semi-positive definite, let us not go semi-negative definite and then indefinite. Let us not go deep into those nature of the quadratic forms of the matrix. It is enough you just remember that it is symmetric and positive definite. Positive definite, there is another way of getting its nature to be positive definite is that all its eigenvalues are positive. Anyway, here you are not going to find eigenvalues here in Cholesky method of decomposition and check whether all eigenvalues are positive and then hence it is eligible for Cholesky method. So when you are asked to find the decomposition using Cholesky's method, definitely it is understood. Okay, right. So the symmetric matrix refers to the matrix we know very well with the element Aij equal to Aj for all I not equal to J. In other words, A equal to A transpose. You know very well. Cholesky decomposition method offer computational advantages because only half of the storage and computation time are required, because in both the Doolittle's method and Crookes method, you need to separately find L and U. But in Cholesky method, one is the transpose of the other, isn't it? One is the transpose of the other. And therefore, it is enough if you find one composition, the other decomposition, one of the two factors, the other composition will automatically be it's a transpose. So that way it is easy. If you find U, it is U transpose U. If you find L, it is L transpose. That's in Cholesky method. A symmetric matrix A is decomposed. So A equal to U transpose U or L transpose. Okay. If it is U, first suppose you are finding U, it is U transpose U. Suppose you find L, it is L into L transpose. So, and that, remember that Cholesky method is possible only when the matrix A is symmetric, and the decomposition for such a symmetric matrix, Cholesky method is possible. Now, how to find elements, entries, how to find, isn't it? We have written L11, L21, L31, L22, all those things are there. Similarly, for upper triangle, all those things are there. Is it right? Well, we have once in L, once in U for Doolittle's method and Crookes method respectively. But all other entries are to be found. For that, you need to have formulas which are to be remembered. So Cholesky method, of course, as before it is it's given the steps. Decompose A such that A equal to U transpose U. Hence we have U transpose Ux equal to B. Set up and solve U transpose some Ux equal to Y. You can have the same Y equal to B, where Y can be obtained by using forward substitution. Set up and solve Ux equal to, instead of Y it is given D. Let us follow the same Y, where X can be obtained by using backward substitution. So this is again the procedure, the step-by-step algorithm in 2 steps. And how do we get the entries? UII is equal to square root of AII minus sigma UKI square summation k equal 1 to I minus 1. UIJ is equal to AIJ minus summation UKI into UKJ k equal 1 to I minus 1 whole divided by UII for j equal to I plus 1 to n. So this is the formula. So when you practically are going to do that, you will not be having much of the summation, all those things, because you are only maximum dealing with a matrix of order 3 by 3. How you are going to get, you are going to see. Okay. Before it's an example of because I couldn't do any editing here actually. It is copy pasted, so I can write here. This is by. So before we come back to this one, I think that's the reason why I have written here. We are going to decompose a given matrix A, which is of order 3 by 3, into 2 factors, that is decompose into 2. That is right product of 2 factors, L and U, of this fashion. This is an example 1. Okay. Now, this is of course you can even this writing using Crookes method decompose A. Example 2, you could not be written here. Anyway, I can just show you here. Okay, so this is just a 2 by 2 matrix, which is getting decomposed. So it is going to be very simple one. Therefore, before it can be actually taken as example 2, or you can see, try yourself. It's going to be simple. Once you learn how the 3 by 3 matrix is done, just look at. So solution to example 1. A equal to LU, where L, just look at. Now the answer is given here. Okay, straight away here the answer is given. L. What is L in Crowd's method? Remember, in Crowd's method, U has the priority. In the sense, U has the upper triangular matrix has the speciality that its principal diagonal entries are one each. Isn't it? Principal diagonal entries are one each. So that you remember. So what are the things you need to find? U2, U12, U13. That's all. Because these are fixed. These are fixed. As far as upper triangular matrix is concerned, for decomposing given square matrix, it is enough if you find for U only U12 and U13, because U11, U22, U33, U23, this should also be found. It so happened it is one here. So U12, U13, U23. These are the only 3 entries you need to find. And these 3 are each equal to 1 by condition. And of course, with the being upper triangular, these are all zeros. Coming to L, and these 3 are zeros by the definition of lower triangular matrix. So we need to find here about 6 entries. L11, L21, L22, L31, L32, L33. How we are going to find? Let's see. Okay. How we got this answer? Let's see. Now, I have shown you the step by step how the entries are obtained. The computations of the elements of L and U matrices are as follows. U12. Let's go back. You need to find U12. Okay. U12, remember, U12, U13, U23. Okay, as far as capital U is concerned. Let's go back. U12 is nothing but you don't have any other source. So it is straight away, because here in crowds, you are giving the speciality goes to upper triangular matrix. Therefore, you start with the U12. And U12 is nothing but just A12. Okay. What is A12? That is first row, second column entry of your given matrix A. So what is A12? This is A11, this is A12. So that is 2. Okay. Next. Similarly, U13. Your U13 is nothing but A13. Okay. Next you are finding U23. Next you are finding U23. Okay. Now, for that, you have to go. The formula is here. Even though immediately after finding easily U12 is equal to A12 is equal to 2, U13 is equal to A13 is equal to 4. Okay. We thought that it is also, it is only thing that we need to find now here is U equal to U23 equal to 1. But you cannot easily find out, because U23 formula is A23 divided by L22 minus L21 into U12. Therefore, we have to go through so many steps here. So we just can't immediately jump to U23. So for the time being, let us now do away with finding, or we will set aside. We cannot find. That's the reason. Okay, right. So we will start finding now entries of L. Okay, what is L11? What is L11? Is A11. What is A11? Is your 1. What is A11? It is your 1. Okay, right. Now, L21. L21 is A21 divided by A11. Okay, so 3 by 1, 3. What is L31? Similarly, A31 by A11. That is 2 by 1, 2. So we have found now L21. Next we go to L22. That is A22 minus L21 into U12. So this formula you need to remember. Okay. L21 into U12. What is A22? Just go back. What is A22? 8. Isn't that? So 8 minus what is L21? We have found 3 into what is U12? It is 2. So 8 minus 6, 2. Next, L32, the same way. A32 minus L31 into U12. Okay. L31 into U12. So what's happening? What is L31? A32. A32. L32 is A32. So go back. What is A32? This is 6. Is it right? 6 minus L31. We already found 2 into U12 is 2. So 6 minus 4, 2. Next we go finding L33. What is A33? A33 minus L31 into U13 minus L32 into U23. So this formula actually, if you go back here, this is Cholesky. So better you can remember this way straight away. So A23, the A33 is L31 into U13 minus L32 into U23. So that is what is L31, A33? What is A33? 13. So 13 minus what is L31? What is L31? 2. What is U13? 4. So minus of 2 into 4 minus L32 is 2 into what is U23? What is U23? U23 actually, this is what we need to find here, and U23 cannot be filled here actually, isn't it? For that U23 you need to find. What is U23? A23 divided by L22 minus L21 into U12. So what is A23? What is A23? 14. So 14 divided by L22 2 minus L21. L21 is 3. L21 is 3 into U12 is 2. So 14 by 2, 7 minus 6, 1. And this one has to come here. Okay. So after finding U12, U13, L11, we are able to find L21, L22, L32, L33. And now that we need to go to U23. So U23, you have to find, then only we can come back to this L33 and you can put this value so that you get 3 here. So now that you fit in everything, you first make these elements 0. First fill in the principal diagonal elements by Crowd's method. In upper triangular matrix, each of the principal diagonal entries are 1. Below that, 0. That is the definition of upper triangular matrix. So you need to fill in now the entries of U12. What is U12? It is 2. What is U13? It is 4. What is U23? It is 1. So just look at now. Thus, upper triangular matrix is 1, 2, 4, 0, 1, 1, 0, 0, 1. Coming to lower triangular matrix, you have to fill in everything as per definition of lower triangular matrix, that is L11. What is L11 is 1. And what is L12 by definition of lower triangular matrix, which is above the principal diagonal element, 0. L13 will also be 0. And what is L22? L22 is L21. L21 is 2. No, 3. L21 is 3. What is L22 is 2. What is L23? L23. What is L23? 0. L23 will be 0, isn't it? Okay. Then L31, L31, 2, L32, 2, and L33, 3. So you have 1, 0, 0, 3, 2, 0, 2, 2, 3. This is how we have decomposed the given square matrix A into L and U using appropriate formulas for finding the entries of both lower and upper triangular matrices by Crouch method. So now that I think you can simply, and now that see the answer is already given, and so the answer was given, and so I have shown you the how that we are getting the components obtained using the formula, and you can check now. So similarly, now you can go for this second order matrix A and decompose into L into U. You get you have for U you have principal diagonal elements 1 1 being 2 by 2. Below it there is only one element, that is 0. So you need to find only U 1 2. Find out. Similarly for L you have principal diagonal elements, that is you need to find L11, L22, and of course L21 also, it should be 0. So if you find using those formulae, you will be getting easily this value, and you can cross check. That is what shown here. After all, A is LU means it is L into U, isn't it? So if you really multiply these two entries, you will get the product. See, it is 2 into 1 plus 0, you get 2. It is 2 into 5 by 2, which is 5, plus 0, you get 5. It is 1 into 1 plus 0, you get 1. And that is 1 into 5 by 2, 5 by 2, it is minus 1 by 2, 4 by 2 is 2. So that is just a justification, which we don't need to show actually. Okay. Now, having come to learn the Doolittle's method of decomposition of the given matrix A into factors of L and U, how we can solve the given system of linear equations. Here are 3 linear equations in 3 unknowns x1, x2, x3. Show the factorization and solve by Doolittle's method. You are given a system of 3 linear equations in 3 unknowns. If there is no factorization word, you know how to solve. Your A is first row 5 4 3, second row 10 9 4, third row 10 13 15, multiplied by the column vector x1 x2 x3, and right hand side column vector 6.8 17.6 13 38.4. And you know how to reduce it to echelon form, then go from the bottom to the top, back substitution method. But here you need to factorize using Doolittle's method and hence solve. Okay, right. So the first show the given system in its matrix form Ax equal to B. First, it can be taken as usual, Ax equal to B, where A, as I just mentioned, B, we know very well. But it is not just A straight away, but A is a LU. LU that you need to find out. Remember, it is Doolittle's method. So in Doolittle's method, you have the special condition for L. You can easily remember. I will tell you how to remember without confusion. Of the two L and U in 2 different methods of Doolittle's and Kraut, where we have the principal diagonal elements 1. You can easily remember Doolittle's method. You have little. So L, lower triangular matrix, has got its principal diagonal elements each equal to 1. And in naturally, the other one Kraut's upper triangular matrix has got the principal diagonals 1. This is how you can easily remember without confusion. So this is being Doolittle's method. A is now LU. So L has got the speciality of its principal diagonal elements each equal to 1. So you know very well, above the principal diagonal element you have 0 0 0, and bottom, of course, well, some authors used to make the entries M also to denote matrix entries, but better I would suggest to you you can go for L for lower triangular and U for upper triangular. It will be convenient for understanding, and also when the any examiner, anyone who just looks into will be able to easily grasp and understand what the student has written. It will be easy for you to. Okay, so it is L21, better you use L, small l, small u. L21, 1, 0. This is L31, L32, 1. This you know very well, just upper triangular matrix. U11, U12, U13. So we need to find in Doolittle's method, we need to find for L only 3 entries and 6 entries for U. In Kraut's method, it is just other way around. In L, you need to find 6 entries, and you need to find only 3 entries. Okay, right. So now let's see. Well, this is Doolittle's method. Here also, you have almost the same formula. You can check. Okay, here is a general formula for finding UIK and MJK or MJ1. M here stands for L. Okay, so U1K, U1K, 1 is fixed, is A1K. K varies 1 to M. And MJ1 column is fixed. It is AJ1, the original matrix entry divided by the U11. U11 is fixed here. Okay, J varies 2 to N. So let us start finding now. So this is a general formula. You can apply, you can find out easily now. U11. What is U11? A11. K equal to 1. What is A11 from the matrix? 5. We don't need to go back. It's given in the matrix 5. What is U12? U12 is A12. Isn't it? What is A12? It is 4. U13 is A13 1. That is 5, 4, 1. Just see. U11, U12, U13 is A11, A12, A13. But remember here, there is a slight change in your formula. You can see in this kind of denominator you have for Doolittle's method, where we had the same in your Crowds also. But you have to have a clear-cut distinction between almost the entries are given to be the same, but you need to check whether they are the one and the same, or if there is any slight change, you have to act accordingly. You have to think of the formula, but you can have some kind of common understanding that if you are able to remember this, and of course these also, whether they are the same for both, or if there is any slight change, you can have some kind of distinction to have an understanding. Okay, right. So we have found U11, U12, U13. Coming to L values. L21 is nothing but, according to this formula, L21 is nothing but J equal to 2, isn't it? A21 by U11. U11 is fixed. What is A21? U11. What is A21 by U11? A21 is 10. U11, A11 is 5. Isn't that? So 10 by 5. U11 is nothing but A11, 10 by 5, 2. And M31, that is L31, is A31 by U11. What is A31? That is also 10. 10 by 5, 2. Okay, right. Now we need to find U22, U23. What is U22? A22 minus L21 into U12. Okay. But these were the things you have found for L in your Crowds method. So whatever you are finding for Crowds will be made use of to find in Doolittle's method. See, where in Crowds you are finding more of L's, and in Doolittle's you are finding more of U's, isn't it? Okay. So U22 is A22 minus M21 into U12. So that is, you can substitute and find out A22. What is your A22? Your A22 is 9. I think I have written. I can check and tell you. The calculations, but I have not. But anyway, you can check A22. What is A22? A22 is 9. 9 minus 2 into 4, 8, isn't it? M2U1 is 2, U12 is 4. Therefore, you have 9 minus 8, 1. Then U23 is A23. What is A23? A23 is 4, isn't it? 4 minus, what is M21? 2. What is U13? 1. So 4 minus 2, 2. And M32, that is L32. L32 is 1 by U22 into A32 minus L31 into U12. What is A32? A32. A32 is 13. Okay, 13 by U22 is 1. So 13. In this portion, you go 13 minus, what is M31? 2 into what is U12? 4. 8. So 18 minus 13 minus 8, 5. So similarly, U33. What is A33? A33 is 15. 15 minus M31 is 2 into U13, 1. So first 13 minus 2, 15 minus 2, 13, 13 minus 13 minus M32 is 5 and U23 is 2. So it is 5 into M32 is 5 into 10. So you have, what did you have? A33, 15, 15 minus M31 into U13, 2. 15 minus 2, 13. Now 13 minus 10, 3. So all those things are found. So just we have A equal to LU is equal to, you can just go back and check L11, L22, L33, each one because it is Doolittle's method. Above the principal diagonals, you have zeros, and below you have found L21, 2, L31, 2, L32, 5, L33, of course, 1. Coming to use U11, 5, U12, 4, U13, 1, and U2, 2, 1, U23, 2, U33, 3. Okay. Now only we are going to shift to the solving now, which is going to be the first time experience for you to getting into the groove of solving 2 times, one after another. So which one we take first, which one we take next, and we get to know the values of ultimately the unknowns that are available in your question. We use this result to solve the system. As A equal to LU, the system AX equal to B is equivalent with LUX equal to B. First step is to substitute UX is equal to Y and solve Ly equal to B as follows. So Ux equal to some Y you take. Okay, so that Ly equal to B. So which is to be solved first now? You have, if you take substitution Ux equal to Y, naturally Lux equal to B becomes Ly equal to B. Is it right? So which will be which is possible for you to solve first? Can anyone tell me? Ux equal to Y or Ly equal to B? There are 2 parts now. If you substitute Ux equal to say Y, it becomes Ly equal to B. So there are 2 parts. One is Ux equal to Y, another is Ly equal to B. U is available, L is available. X is to be found. So if suppose you take Ux equal to Y, what will happen? U is available, X should be found. Where is Y? It's not there. So you go to Ly equal to B. B is available, L is available, therefore you can find Y. So you have to take Ly equal to B first. Now, Y1 equal to 6.8. How did you get this one? Just see here, you go back here, Ly is equal to B. Take this, okay? I just show you. Now, what is the meaning here? Actually, Ly is equal to B means what? How did you get this one? What does this mean? What does this mean? Your L is 1, 0, 0, 2, 1, 0. Then 2, 5, 1 multiplied by what is your Y? Y1, Y2, Y3. Is equal to what is your B? What is your B? It's given in your question, right hand side, 6.8. $17.6, 38.4. Isn't it? So now what is that? How will you do the multiplication? 1 into Y1 is your 6.8. Just look at. Next, 2 into Y1 plus 1 into Y2. 2 into Y1 plus 1 into Y2 is equal to 17.6. So now you substitute for Y 6.8, this becomes 13.2. So you have 4.2Y2, 2Y1 means 13.6. So Y2 will be 17.6 minus 13.6, 4. Then 2 into Y1, 6.8 plus 5 into Y2. This is 20. This is 13.6. So you have 33.6. So 38.4 minus you get 4.8. Isn't it? So this is how you are now multiplying. Straight away you are getting first one Y1 value only. Substitute in the second. It is not back substitution actually. It's actually forward. It is straight away. It's ordinary multiplication only. Just you can see 1 into Y1. Isn't that plus 0 into Y2 plus 0 into Y3? I can simply say 1 by 1 equal to 6.8. 2Y1 plus 1Y2 plus 0Y3, which is 17.6. Substitute for value of Y1, you get Y2 equal to 4. And third, 2Y1 plus 5Y2 plus Y3 is equal to 38.4. So Y3 equal to 4.8. Having substituted for Y1 as 6.8, Y2 as 4. Now you are able to get the unknowns that you have introduced, Y1, Y2, Y3. You go back to the first one now. Now you take Ux equal to Y. So what is Ux equal to Y? It is now, this implies your U values, your X1, X2, X3 is equal to Here, this one, your 6.8. Four and 4.8. For this portion. So this would mean what is your U, what is your U541? You just look at where U is here, isn't it? So this is your U. So you will get now 5x1 plus 4x2 plus x3 is equal to y1. That is 6.8. Next, you go 0x1 plus 1x2 plus 2x3 is equal to y2, which is 4. Next, finally, you have 0x1 plus 0x2, not necessary, 3x3 is equal to y3, which is 4.8. So now it is actually back substitution, isn't it? So when you have x3, 3x3, 4.8, x3 will be 1.6. Substituting this as 1.6, you get 3.2. So x2 is 4 minus 3.2, 0.8. And 5x1 plus this is 4 into x2, 3.2 plus 1.3, 4.8. 6.8 minus 4.8 is 2. So 5x1 will be 0.4. Thus, you are having x1 equal to 0.4, x2 is equal to 0.8, and x3 is equal to 1.6. You can finally, of course, list the solution set in that order of x1 equal to 0.4, x2 is equal to 0.8, and x3 equal to 1.6. So, do you have any doubt here? Apurva Ranjan, are able to follow this decomposition first and then making use of them separately, introducing a new variable y and solve with that y as unknown with the given b and your L. Having found y, go back to ux equal to y, u is there, y is found and x can be found. So finally it is ultimately given the system is a system of linear equations in the variable x. So therefore the unknowns are x1, x2, x3 whose values are found through two-pronged strategy. That is in 2 steps we have found after decomposition. This is by of course Doolittle's method. So the decomposition process slightly gets varied, changed with the various the entries that you are finding using different formulae. Otherwise, the idea is going to be the same after solving first Ly equal to b and then ux equal to y. Is it clear now, Apurva
Yes,
Ranjan?
sir.
Is it clear? Okay, right. Yeah. Cholesky's method. So here what's happening? Shall we have a break for it? Shall we 5:23?
Sure, sir.
Okay. Shall I resume the class? Hello? Ranjana? Are you ready? Hello?
Yes, sir.
Fine, good. Now let's go to the last method, Cholesky method. Show the factorization and then solve. Okay. The matrix form of the given equation, given system of equations is X equal to B, where A equal to B equal to what we originally write. Of course, X also you can write X1, X2, X3 column vector. Cholesky factorization will decompose A as L into L transpose. Either you can write U transpose into U or L into L transpose, so that the finding of entries of the matrix will be confined only to one of them. It is enough you find L so that you multiply with its transpose. Of course. Otherwise, if you find U, it is U transpose into U. That order is important. Okay. So here let us take L into L transpose, where L is the lower triangular matrix. No other special condition of having any principal diagonals. So it is lower triangular matrix and it's a transpose. That is the way that Cholesky method gets different, is distinguished from the other two. Now, and of course, we have therefore an entirely different set of formulae for finding the entries. Look at formulas are given. L11 is, in the previous two, it was just A11. Isn't it? So it is root of A11. And MJ1, of course, again here M is taken for L. It is only L because here we have taken everything only L. We are confining ourselves to, so that the other one is transpose. So here, when you are having L, it should also be N. Better let there not be any confusion. Therefore, it can also be taken as L. Okay, right. LJ1 is AJ1 by U11. Here you may be wondering what is U11. U11 is again nothing but A11. U11 is nothing but because here we don't have U at all. Why U is given? Suppose you have taken U upper triangular. That is also possible, isn't it? That's why. Therefore, we can just write what U11 means, isn't it? That is always better. So what's happening now? U11 is A11, right? L11 is its root. And LJ1, AJ1 by U11 is fixed. That is A11 is fixed. So J equal to N, etc. And LJJ is root of AJJ minus summation LJS square, where the second subscript S varies from 1 to J minus 1. And J starts from 2 to N. LPJ 1 by LJJ into APJ minus summation LJS into LPS P equal to J plus 1 to N, J greater than or equal to 2. So if you just have a common formula like this, definitely when you are having more than 3, 4, 5, I mean rows and columns, then all these things in general you don't have to worry about. Otherwise, it is easy for you to remember if you just look at this 3 by 3. Okay. So here, of course, you can get this convinced and ensure that it is following this formula only. Let's see. L11. L11 is root of A11. What is A11? 9. Is it that? A11 is 9. So I will just take this. You don't need to go back every time. Root 9, which is 3. This is root 9 because A11 is 9, so 3. And L21. L21 is A21 by A11. What is A21? A21 is 6. So 6 by 3, you have 2. Not 3 actually. L21 is A21 by A11. Here is a change actually. It is not U11, it is L11. It's not U11 because U11 is root of A11 and L11 is root of A11. So it is only U11. Sorry, I think. Since we have taken straight away L, the formula also we take only, it is L11 fixed. It is L11. AJ1 divided by L11. Okay, this is your LJ1. AJ1 by L11. So what is here? L21 then A21. A21 is 6 in your data. 6 divided by 3. So you get 2. Then L31 similarly 12 divided by 3. So you get 4. Then so we have L11, L21, L31. Okay, that is first column, first row, first column, second row, first column, third row, first column. Then L22. Now you go to principal diagonal elements. L22. It is root of A22. Just look at L22 is A22 minus LJS. That is J is 2. Okay. S starts from 1. So L21 square. That's all. You don't have any more summation because if you go for summation, you will have the extra 3. Isn't that? J will go to the next value 3, but you don't have 3 here. Is that right? So it is just L21 square. So what is A22? A22 is 13 minus what is L21? L21 is 2 square. 2. So 2 square. It is now 13 minus 4, 9, root 9, 3. Next is L32. L32 is 1 by L22 into A32 minus L12 in L12 and 21 into this formula. You just look at L32 PJ. So this is LJJ. That is J is 2 here. Therefore you have L22. APJ. LPJ is your A32 minus summation LJS. Okay, S starts from 1. What is J here? 2. So L21, right? Then it goes into P. P is your 3. So L31. That's all. So you have now 1 by L22. That is L22 is 3 in the denominator. In the numerator, what is A32? A32 is it's given 11 minus L21 into L31. L21 into L31 is 8. So it is 11 minus 8, 3 divided by 3 equal to 1. Next, L33 in the same fashion here. But here you are having two subtractions. Why? You just see that. L33 is A33 minus L31. S starts from with 1 square plus. Now you can think of summation plus, because you can think of now increasing S to 2. S starts from 1, you can go to S3 to L32 also, because L32 is available. So L32 square. Then you may ask one question, why it is minus? Because minus of summation. So minus minus. Will you go to next one? You will not be able to, because next one, if you have, it is only 3 here. Okay. Next you can have, of course, minus L33 square, but you don't have L33, isn't that? That is what you are finding actually. So we cannot have here L33 square. So A33 minus L31 square minus L32 square. So it is A33 is 26 from the data. L31 is 4 square 16 minus L32 is 1. So it is 16 minus 16 minus 1 minus 17. And this is 26. So 9 root 9 3. So thus we have found all the entries. Therefore, what's happening now? It is now A equal to, we have found now L entries, L11, L11, 3, L21, 2, first column. Okay, L31, 4. Then, because it is a lower triangular matrix, because you are interested in finding L11, L21, L31, then L22, that is 3. You know very well, L3, L23 will be 0, and of course, L12, L13 will be 0 because of the definition of lower triangular matrix. And coming to the last two, L32 is 1, and L33 is 3. That's also, it's enough if you find only these 6 entries. So, in Doolittle's method, you are finding 9 entries. What's happening there? 6 UIJs and only 3 LIJs, so that 9. In crowds, it was LIJ 6, UIJ 3, so 9. But in Cholesky method, only 6, because the other one is it's a transpose. So first column 3 to 4 will become first row 3 to 4. Second column 0, 3, 1 will become 0, 3, 1 second row. 0, 0, 3 third column will become 0, 0, 3 third row. So when this is L and this is its transpose, and thus A equal to, it is not LU actually here, L transpose. Actually, of course, LU, but it is not. In Cholesky method, U is nothing but transpose of L. Okay, so which you can better clearly write. And better write. Otherwise, it will confuse you, because it is not that we have found U. And in Cholesky method, of course, A is LU in general, but in Cholesky method, you don't need to separately find U at all, since U is L transpose for Cholesky method. Okay. So you have okay. So as usual, L transpose X equal to B. Substitute. We had LU X equal to B and LU X equal to Y, all those things. So in the place of U, you are having L transpose. Anyway, it is the matrix that we have found already. In the place of U, we have L transpose in Cholesky method. All other things remain the same. So first we will take Ly equal to B. Okay. So what is Ly equal to B? I'll just show you. What is L300, 230, 413 into Y, Y1, Y2, Y3. What is B available in your system of equations? Right hand side, constants, 5.8, and not 5.8. What is given in the question? 17.4, 23.6, 30.8. So what's happening then? 300. So 3y1 only. 3y1 is 17.4 means y1 equal to 5.8. Then you had a 2y1 because next is 230. So 2y1 plus 3y2 is equal to 23.6, where y1 5.8 if you substitute, this is 11.6. So you will have here 12. So 3y2 is 12 means y2 is equal to 4. And 4y1 plus y2 plus 3y3 equal to 30.8. So 4y1 means 23.2 plus 4, 27.2. So here if you substitute, it is 3.6. 3y3 equal to 3.6. Therefore, y3 equal to 1.2. So now that you have the inner composition, in the sense L transpose X equal to Uy, Y. Okay, because in the place of U, you are having L transpose. Now, what do you have now? What is the L transpose now? 324031003. So back substitution. That is 3x3 is equal to your right hand side y3 1.2. So that is equal to, therefore x3 is equal to 0.4. Next we had 0x1 plus 3x2 plus 1x3. That is 3x2 plus x3 is equal to right hand side y2. That is your 4. So when you put x3 equal to 0.4, it is 3.6. So x2 equal to 1.2. Then 3x1 plus 2x2 plus 4x3 equal to 5.8 y1 value. So it is now 3x1. X1 is to be found. So 2x2 2.4. This is 1.6. So you have 4. So 3x1 equal to 5.8 minus 4 1.8. So x1 equal to 0.6. Therefore we can write, it's better. We can write, therefore always give the conclusion. Therefore, the solution is always write in the order. X1 is equal to 0.6. X2 is equal to 1.2 and x3 is equal to 0.4. So this is again, as we just mentioned, so just a recapitulation. To find, this is very important, to find inverse of given matrix using Gauss-Jordan method. means you consider augmented matrix AI, because you know very well inverse finding is related to your product A into A inverse equal to I. So that gives rise to considering an augmented matrix AI. So A is your matrix given, I is the unit matrix. Okay. Then whatever you do on the left hand side, that is you are writing the coefficient matrix, then you are making a demarcating line. Then you also write the unit matrix. Supposing it is a of order 3 by 3, you write 1 0 0 0 1 0 0 0 1. Then the elementary row operations are done throughout. Then finally what's happening? You must be able to ensure that here it is not just bringing in only one form of triangular form to reduce it to echelon form, but we do two sets of operations, in the sense bringing to both lower triangular and upper triangular. So first, as usual, you know very well, you will do two sets of operations, two operations keeping R1 fixed by doing on R2 and R3. Then doing on R3 in terms of fixed R2, you have one set of operations, we can call it. Then what we will do then, we will go back to keeping R3 fixed, R1 and R2 operate. Then keeping R3, R2 fixed, operate R1 and R2. Exactly ulta. So that you will have only principal diagonal elements. You will have on the left hand side to ensure that 1 0 0 0 1 0 0 0 1. That is only principal diagonal elements. You will have one each. All other elements are zeros on the left hand side of the demarcating line. And you have naturally will be left with a 3 by 3 matrix. And that is the required inverse of the given matrix. So to cross check after having done this much, better you take your original matrix given A and the matrix that you have found at the end on the right hand side of the which is A inverse, A inverse. So you take A inverse, you multiply this. If you are getting unit matrix, then your answer of A inverse is correct. Okay, so here is an example. Finding inverse matrix by Gauss-Jordan method. Find inverse of A minus 1, 1, 2, 3, minus 1, 1, minus 1, 3, 4. Consider the augmented matrix A, comma, I. So you have the 3 by 3 matrix, put the demarcating line. It's 1, 0, 0, 0, 1, 0, 0, 0, 1. Then start operating on what is our first aim? To have your second row first column element to become 0. That means we need to do elementary row operation on all elements of R2 keeping R1 fixed by just checking the very first element, because this is where we want to make it to 0. Isn't it? That means what is the connection between these two? You have to multiply minus 1 by 3 and add it to 3. That means R2 elements are to be added to R1 by multiplying by a constant 3 of all elements of R1. That's the meaning. So R1 is R1. See, row 1 is row 1. This is how normally we write R1 arrow mark. So R1 is R1. That is fixed. That is the base on which you are doing elementary row operations. So row 2 throughout plus 3 times row 1. So 3 plus 3 into minus 1, 0. So it has to be done throughout now. Minus 1 plus 3 into 1. So 3 minus 1, 2. 1 plus 3 into 2, 6 plus 1, 7. 0 plus 3 into 1, 3. 1 plus 3 into 0, 1. 0 plus 3 into 0, 0. The same way you have to do for R3 in terms of R1 only. Okay. For that, now this has to be made to be 0 now. That is first column, third row. Minus 1, it is first element is minus 1. So how will you get 0? R3 minus of R1. Minus 1, minus of minus 1, plus 1, minus 1, plus 1, 0. Same is to be done throughout. 3 minus 1, you get 2. 4 minus 2, you get 2. 0 minus 1, minus 1. 0 minus 0. Then 1 minus 0, 1. That's all. This is one set of operations of R2 and R3 on R1. Next, R1 is R1, that is over. As usual, because already it is the base, so nothing to worry about it. Now R2 is to be taken as the base. Now R2 is also standardized, fixed. So you have to do only one operation on R3 in terms of R2, not R1. R1 role is over. So because you are now interested in getting this element 0. For that, you just check with the immediate element of R2. 2 minus 2, 0. That means every element of R3 minus every element of R2. Simple in this case. So it is, of course, 0 minus 0. 2 minus 2, it is 0. 2 minus 7 minus 5. R1, R2, you have to write the same. Only you have to think of R3 now. Minus 1 minus 3 minus 4. 0 minus 1 minus 1. 1 minus 0, 1. So this is what normally we do. And of course, in Ax equal to B, you have x3, this is x2, x3, this is x1, x2, x3. Here you will have only one constant vector and you will solve. That is what we have seen now in decomposition also. But here it is matrix, matrix, finding inverse of a matrix. So now we have to reverse, isn't it? Just look at what's happening now. What did we do now? Just to go back, you just look at. Look at the first row. In first row, before we think of making here, actually, you got to get 0. Here also, you got to get 0, isn't it? Yes, sir. So, and this should also become 0. Like your this triangle becomes this 3 becomes 0. Here also, you must get a 0, isn't it? So we have to do R1 in terms of R3 because now R3 is standardized. Okay, right. So, of course, R2 you can do R2 and R3. I mean R1 and R2 in terms of R3, then R2 in terms of R3, right? So what we will do now, before we go to do that, you can ensure that if there is 1, it is better here in the very first row, first column. If it is anything other than that, you can have some simple multiplication or division, whatever it is. So you have minus 1 here. If it is becoming plus 1, that's better, isn't it? So multiply through this row by minus 1. So you get 1, minus 1, minus 2, minus 1, 0, 0. So R1 is multiplied by R1. What did we do here? We have not done then something, no other elementary operation now. I mean, row operation. It is only within the row. R1 is now R1 into minus 1. R1 or divided by minus 1. You can say divided by minus 1. R2, similarly, what do? We go to R2. R2, we just see here 2. Here we need to get 1. Isn't it? 1, 1, 1. So let us divide R2 by 0.5. That is, you multiply by 1 by 2. You multiply by 0.5. Okay. So as to make it 1. Or you divide by 2, whatever it is. Similarly, here divide by minus. So here R2 is R2 multiplied by 0.5. R3 is R3 divided by, minus 5. So we have made this 1, 1, 1. So that correspondingly you have changes here also because of division by minus 1, because of multiplication by 0.5, and this is division by minus 5. Okay, now we go for operation because here we need to have 0. Okay, as here you have made 0 first, here you have to have 0 now. So R1 is R1 plus 2 times R3 because you had R2, R3 in terms of R1 in the first set. Now in the second set of operation, it is R1 and R2 in terms of R3. R3 is fixed. So because it's already 0, 0, 1 fixed. Now no more simplification. So R1 you have to have 0 here, which is possible minus 2 plus 2 times R3. Same thing you have to do throughout now. So 1 minus 1 you will have the same. This becomes 0. This is minus 1 into 1.6. Sorry, minus 1 plus 1.6, 0.6. This is 0.4 plus 0, 0.4. This is minus 0.4 plus 0, you get minus 0.4. Similarly, R2 is R2 minus 3.5 times because you have 3.5 here. So you just see that R3 is 1. So 3.5 times R3, which is to be subtracted from R2. So you get this becomes 0. So correspondingly, you have changes. R3 is R3 only. Right? So now you just see that only one more change you have to do that. You divide throughout by. Next, you have to do one more operation. That is, this is to be made 0, isn't that? So you have to have, now you don't need to go to R3. R3 is already fixed. R2 is also now fixed. So you go to R1 and R2. Minus 1 plus 1. So that is R1 is now R1 plus just R2. So it is 1 plus 0, you get 1. Minus 1 plus 1, you get 0. 0 plus 0, you get 0. 0.6 minus 1.3 minus 0.7. 0.4 minus 0.2 plus 0.2 minus 0.4 plus 0.7 plus 0.3. R2 is the same 0, 1, 0 minus 1.3 minus 0.2 0.7. R3 is the same 0, 0, 1 0.8 0.2 minus 0.2 and this is your A inverse. So what has happened now? I'll just show you A comma I augmented matrix you started with has now resulted in the augmented matrix I comma. So what is on the right hand side? It should be A inverse. It is A inverse.
Yeah, sir.
Therefore, you need to write one sentence. Therefore, the required inverse of the given matrix A is A inverse equal to, you should write out specially, separately. Therefore, A inverse equal to this matrix. Minus 0.7, 0.2, 0.3, minus 1.3, minus 0.2, 0.7, 0.8, 0.2, minus. That you have to separately write. And that is the result. Is it clear now? This is very important.
Yes, sir.
Okay.
Clear.
Right. Wow. Um, now, well, wish you all good luck in all your exams in general and in particular LAO.
Linear. Yeah. Thank you, sir. Thanks for your
Anything,
wishes.
we've got some more minutes are left. If you've got any other clarification you want to seek, any other doubts to be clarified, I'm happy to do it.
Fine for now, sir, because got all the theory, just need to practice now.
Okay, good. Carry
Yeah.
on. Okay.
Yeah.
Gauss elimination by pivotal. Okay.
Yeah.
And this inverse Cramer's rule, linear
Doolittle
dependence,
method
independence.
and all.
Okay. All those things. This eighth contact section you don't need to worry about because it is just
Okay.
done only today, right?
Okay.
Okay. All the best then.
Thank you, sir. Thank you so much, sir. Have a great day.
Okay. Navina, there is one more candidate. Rita Navina. Any doubt? Anything you want to ask?
So, like, do you have posted the model paper of previous for our reference? Have you ever posted in Teams or e-learning portal?
No, no, I am not able to hear you.
Am I audible,
Just
sir?
Yeah, yeah. Once again, repeat.
Like, am I asking, like, have you ever posted um, uh, model paper in e-learning or Teams for our reference, previous papers?
Previous year question paper. Yeah, that's what no. The Apurva Ranjan had made a request some time back, I think a week back. Normally, we don't have any idea or something that we are in possession of it. So I wrote to the coordinator. I think intern coordinator has written to the person concerned. I thought that it would have been issued. Normally, it will be made available in Taxila portal. Previous year question papers in general. I don't know what has happened to it. That's what I was talking to him also. And he said it is not yet available. Anyway, I will find out from the coordinator and see that it is coming there. If that is coming in, I will just post an announcement in the Teams you can look forward to. Then you can go to Taxila and look forward to. Okay. Right.
Okay, sir. Thank you.
Anyway, see, don't bother about all those things. This is the thing, You concentrate at what all the things that I have. I told you about giving importance to from exam point of view. Practice. Right?
Okay,
Okay,
sir.
sir.
Okay. All the best. Wish you good luck.
Thank you, sir.
Okay. Your good efforts should definitely bear. You have been attentive. Do it. Do good. Stop sharing then.
Mm-hmm.
Is it okay? Right.
Yeah, yes, sir. Fine, sir. Fine,
Okay.
fine.
Okay. Thank you.
Okay, sir. Thank you, sir.
Thank you. Okay. Fine.
Yeah.